So, as I promised, I'm going to teach you second and then higher order systems. Through that, I'm going to teach you oh my god. I'm going to teach you that R, L, and C circuit Vin plus minus resistor, inductor, and capacitor dynamically equals to spring, damper, and mass M. Now you have mass here. In the previous case, first order system, you had no mass. And this is dynamically equals to tank of the water. Two tank of water in series. Two tank of water. So if here is a H1, this height. Here is H2. This contraction can be given as RT1 tank resistor. This contraction, like as your sink, is RT2. This is capacitance of this tank, CT1, CT2. And you have inlet flow, Q in, and outlet flow, Q out. And all of these are second order system, and they are dynamic the same. So when I drive this and I'm gonna apply the different inputs to the system, I don't care which system you're talking about. I'm talking about generally second order systems. So let me derive these two first and define the new parameters. Actually, I taught the parameters in the vibration course, but those of you that didn't pass the vibration course, I have no idea how the system allowed to come to this course. Okay, but I'm going to teach here. So this one, RLC circuit, we name it RLC circuit, based on the voltage Kirchhoff law, Vin equals to VR plus V of inductor plus voltage of the capacitor. Here is VR, voltage of this, and the voltage of capacitor. What we're gonna find? We're gonna find the closed loop transfer function of the capacitor voltage over input voltage in frequency domain. Okay, I told you that Vc is 1 over C integration of I dt. If you go to electric circuit 1 you passed, or the physics of high school, VR, inductor voltage, is L inductance di over dt. I think that all of you passed electric circuit 1 in the university, and you know this. This is inductance, and this is capacitance, that's right. So we're going to use that. We're going to say Vn equals to, and Ohm's law says from elementary school that for middle school it says Ri. So we're going to set Ri plus VL is L di over dt plus Vc. So from here we know that from this relation, as I wrote, and you have in your notes, I's can be as C dVc over dt. Remember the first order system. So I'm going to replace this I here and here. So Vn gonna be R C dVc over dt plus L time derivative of C dVc over dt plus Vc. Good. C is constant coming out, for God's sake. Here we go, C coming out, Cl. So what you get is Vn gonna be Rc V dot C to first time derivative plus Lc dt dt second time derivative V double dot C plus Vc. Bingo. Now you tell me, if you remind that I told you if I want to go from time to frequency domain, what you gonna do? What you gonna do, guys? Laplace transform. Now remember, of one time derivative is gonna be S. You have your notes. Second time derivative gonna be S square. So by assuming that V at capacitor voltage at time 0 is 0 and the time derivative of the capacitor is 0, if you apply there, can I go to next page? Everybody? Yes?
Yes.
If you apply there, you're gonna have LCS square VC S, obviously I'm dropping this, plus RC plus RCS VC, S comes here, S square, and VC plus capacitor voltage is equal to Vn. So you get that the closed transfer function of capacitor voltage over input voltage is 1 over LCS square plus RCS plus 1. You got it? So this is second order system, guys, because your time domain is second time derivative. Your S domain, the highest is 2, S square frequency domain. This is second order system, as I promised. But I'm gonna play a little with that. I'm gonna factor out LC. Gonna be S square plus RC over LC, S plus 1 over LC. Then I can write this as this. I have intention. I'm not stupid. I'm gonna write as this 1 over LC in S square plus this C with C goes to New York. You have R over L S plus 1 over LC. And now I introduce you from vibration. Bear with me. Why? When I'm teaching you the mass spring and damper, except from me. Those who had vibration with me in the previous semester, this is, we name it as 2 zeta n. Natural frequency, because the pendulum, natural frequency, and this is damping ratio. Damping ratio from vibration course is being defined as C over Cc. Damping over critical damping. Critical damping. I'm gonna introduce in the mass spring and damper. the next example. Okay, bear with me. So the unit of this is 1 because damping over damping. So damping ratio has a property. Properties has non-dimensional parameter. Non-dimensional parameter. And I'm gonna name this as national frequency square. They are the same parameter. I'm gonna name as this as national frequency square. And interesting to see that your RLC circuit, like as the massive spring damper, okay, has damper. Interesting, right? Has damper. Like damper of your car tire over your car tire, we have damper. That's right, to remove the oscillation. You know, the damper function is to remove oscillation. Is to remove or damp oscillation, as its name says. Oscillation. When you pass the vibration course, you're gonna go there in detail. So, as I promised you, I can write second order closed loop transfer function of this RLC circuit as the universal expression natural frequency, and its natural frequency is radian per second, its unit from dynamics course. Natural frequency means system oscillates by itself without an excitation force. Okay, look at the pendulum. Remember in the pendulum problem, natural frequency of the pendulum was, you have in your notes, G over L, gravity over L. And it was oscillating by itself forever, remember? But when the damper arrives, damper gonna vanish that. So is S square plus 2 zeta omega ns plus omega n square. This is second order for this RLC circuit. By knowing that zeta is resistor or inductance and natural frequency is 1 over LC. We got it, everybody? Second order. Now we are in the control. We are way behind. We are way done with the vibration course N520. We have to take this to the realm of control, realm of coding and the simulating and real control. So if I want to plot the block diagram of this and take it to the MATLAB simulating and connect the MATLAB simulating to the real device, I have to put the unity feedback by assuming that the sensor is ideal. So this is V in, this is VC, unity feedback, as we are repeating, plus minus. Here must be what? Open loop transfer function, G. So you have to, when you go to Simulink, you have to find that. So let's find that together. VC over Vn was omega n square s square plus 2 zeta omega ns plus omega n square. How to find this? I taught you a million times. From general formula, what's that? G1 plus G. I'm skipping the math, I know from my mind. If you do that from here, you find G gonna be omega n square in s square plus 2 zeta omega ns. Don't put this one here. You have to put G. Here we go. You got it, everybody? I'm gonna do on the simulink the next class. Don't worry. Okay? For going deep into the concept of zeta and omega n, and you don't believe that, but I'm telling you, we're gonna design controller based on two parameters. I swear. We're gonna design controller based on two parameters, zeta, omega n. And we are making everything universal. We don't care which system we are talking about. We are talking about zeta and omega n, friends. You see. So let me provide a proof that this is equal to this. And here I'm going to talk about zeta and omega. Second order system, mass spring damper. So for the mass spring and damper, suppose this is K, linear spring, linear damper C, mass here M, and you have a force K F of T. This K is the same K, is number. Huh? And when you apply the force, this mass moves, displacement of X. The simple model of your car suspension system over your tire is the spring and damper, the modern car. Here we go. Okay? So what I want to find? I want to find X of S, closed loop transfer function, over F of S, closed loop transfer function. You know, from vibration or dynamics, you have to cut the system from here. When you're pulling to the right, you have a reaction force from spring and damper. Even that you're not mechanical engineer, when you were a child and you were pulling a spring, it tries to pull back your hand. So that's a reaction force. This Kx, here is X is 0, that's right. And Cx dot. Now I'll take you to the ME 220 course that you passed here at San Diego State, and calling the Newton, Mr. Newton, and say some of the forces in X direction is mx double dot. Now you have m, mass, despite the first system that wasn't spring and mass. So it's mx double dot equals to minus cx dot minus kx plus kf of t. See, here's positive this side, this is eudacium, here's negative, this is positive, negative. If you rewrite that, you're gonna get mx double dot second order system, because you have 2 time derivative, plus cx dot plus kx equals to k f of t. Now if you divide both sides by m, you get x double dot plus c over m x dot plus k over m x gonna be f of t. Now you know it, hopefully from at least ME 432, if not vibration. The name of this is the natural frequency square. So natural frequency of mass and spring is k over m. Just go k over m. And then this damping coefficient divided by m is 2 zeta omega n. Oh, it's very similar for the RLC circuit. Can I go to next page and introduce you about the zeta? Yes?
Yes.
Good. So, being said, you have x double dot plus 2 zeta omega n x dot plus omega n square x is equal to f of t. We are close to the closed loop transfer function, but I told you zeta, it's time to introduce that to you. It's C over critical damping, I told you. For now, accept from me if you didn't pass vibration, and I don't know why you are here, okay? But accept from me that CC, I'm gonna teach later, is 2 km. I'm gonna teach you why later. Root square of stiffness in mass. So that's why when you say 2 zeta omega n, it's say 2 multiplied by C km. Omega n was what? Root square of km. 2 with 2 goes to hell. This k with this goes to hell. So the result is C over m. See here? C over m. This is definition. Here we go. Damping ratio. So normal ground in time domain. I want to take you to what? Frequency domain. What I have to do, you tell me. Laplace transform by the assumption of the mass at the initial time is 0 and its velocity at time 0 is 0. For simplicity and sake of teaching, you get s squared x of s, second time derivative, plus 2 zeta omega ns x of s plus omega n squared x of s is equal to f of s. And you know that simply that the closed loop transfer, I'm dropping s because we know that x over this is omega. I'm sorry guys, why I did this, I'm stupid. I divided k over m. I forgot because I'm teaching from my mind. I have no notes, guys. So k over m is the same here, that's right. So here you have to put, here you have to multiply by natural frequency square. And here is natural frequency square. You saw what happened? Because I divided everything by m. Huh? So, gonna be natural frequency square, s square plus 2 zeta omega ns plus omega n squared. Oh, have you seen this? Yes, 10 minutes ago for RLC circuit from electric circuit 1 course. So they are the same system dynamically. Here we go. Here we go. Here your closed transfer function was Vc over Vn, the same statement. But the zeta and omega and they have the different values. Okay. Here is the same, but your zeta here is C over 2 k over m, and the omega n natural frequency is root square of k over m. Here we go. That's why you see that your RLC circuit gonna oscillate and vanish. I'm gonna teach you by mathematics. So what I proved you that these are the same system. Okay? If you try this, I don't want to kill your time on this. I'm just going to give you the general formula. You can derive that. So for the two tanks in series, guys, as we did previously, let me plot the figure here. For the first order systems. RT1, RT2, CT2, CT1, here's H1, and here's H2. I'm just replotted here. Q in, inlet flow, Q out. So what I want to find, I want to show you that Q out closed loop transfer function over Q in. And I bet $1 million you're gonna get the same result. It's a second order system. Okay? How? Remember in the previous class that we said H equals to voltage, resistor is equal to resistor, current was what? Flow rate. In system dynamics and modeling, ME432, they had to teach you. Even this semester that you are taking, they have to teach you. Get it, everybody? So for the first tank, so when you have a Q in, you have an intermediate bridging flow here between these two tanks. I say Q. Like as the previous not cage, because I said I is equal to V is equal to over R from the Ohm law. Here I said the Q is equal to H over R. Remember for the first order system. So the first tank, what affects in the R is Q is equal to H1 over Q. Yes. Is this right? Think about this. I'm going to give you 2 minutes. I want that you tell me if this is right or not. Think about this. Huh? Everybody? Is this right? Hmm? Obviously no, guys. Okay? Because this current or flow is between two tanks. So you have delta H or potential difference. So that's why you have to look as H1 minus H2 over and over R T1. Here we go. We got it? So because it's between two potentials Q. This is relation number 1. Huh? And also I taught you that the I is equal to from the capacitor dt. So you're gonna have the same. You're gonna have Q again, C of tank dH over dt. So for tank 1, still you're in tank 1. So Q is what? Net flow. So Qn minus Q equals to CT1 dH1 over dt. Relation number 2. Now let me fix this, guys. You got it, everybody? Now for tank 2. Tank 2, you get that Q out is only affected by H2 and R2. So it's going to be H2 over RT2, relation number 3. And for this relation, you're going to have Q minus Q out equals to what? CT2 dH2 over dt. This is analogy with the electric circuit. So 4. So what we want to find? We want to find Q in over Q out. You got it, everybody? So I'm going to give you a couple of minutes that you drive it as a homework now. So please do at home, but I'm going to tell you again. If you do at home, you can just Google it. If you look at your book, Q out over Q in, again gonna be natural frequency square S square plus 2 zeta omega n S plus omega n square, but different omega n and zeta for the system. Just play with these 4 and you're gonna find it. You got it? Yeah. So, being said, you see that these 3 are the same system, second order system. Now let us just stick to the math of that to see how they behave. Knowing that now we know, generally speaking, output over input closed loop transfer function is second order system like this, second order system like this. And from high school, you know, this is second order equation. So we're gonna have 2 poles. We're gonna have 2 poles, P1 and P2, because we said the name of this system, roots of the denominator are the poles, second order system. And you know how to solve it from high school, right? You said P1 and P2 equals to minus B plus minus B square minus 4AC divided by 2A. Your A is 1, your B is this, your C is this. So it's gonna be minus 2 zeta omega n plus minus 4 zeta square omega n square minus 4 omega n square divided by 2. This equals to, if you factor out um, minus 2 zeta omega n plus minus, if you factor out 4 omega n from here, it's going to be 2 omega n. That's right. It's going to be zeta squared minus 1 divided by 2. This 2 and this 2 and this 2 goes to New York, and you get you have two poles of the system, second order system. Gonna be minus zeta omega n, can be RLC circuit, can be spring mass damper, can be two tanks in series. I don't care. This is control class. Plus minus omega n zeta squared minus 1. Having that, we're gonna analyze in the complex plane. We have three scenarios. First scenario, if damping ratio is smaller than 1, means that your car tire damper is very weak. We name this in vibration and control as underdamped system. The damping of your car tire is not enough. After passing a bump, you're gonna feel vibration a lot. Physically means that. This technical name is underdamped system. If zeta is smaller than 1, zeta square is smaller than 1. It says that zeta square minus 1 is smaller than 0. And it says that this is a negative number. We don't have it in mathematics. So we have to write as this, zeta omega n plus minus I is what? Put the square of minus 1. Omega n 1 minus zeta squared. See, I switched the place. But from vibration, if you didn't, I'm going to introduce now. Natural frequency damping. So it has a name, technical name. The name of this is damped natural frequency. We're writing as omega d, damped natural frequency. Damped natural frequency. So when your system is underdamped, so the poles of the system gonna be minus zeta omega n plus minus two poles I omega d. As we are not blind, we see that the poles has two parts. One real part which is negative, and imaginary part. Now let me go to the complex plane. Can I go to the next page? Everybody? Yes? So if I plot this, because this is control class, not vibration. So this is imaginary and the real. So it says two poles. We are showing poles by cross. Negative real part. Here it go. Here is minus zeta omega n. And one of them is plus I omega d minus I omega d. So the two poles, we're gonna show that these are the poles. This is one pole, this is another pole. The student that was in the class was asking me that I have a problem in control. Can I have underdamped system for robotics? Is it still here today? Okay, guys. The name of this response, sir, is the system has a pair of complex conjugate poles. A pair of complex conjugate poles. This is very good for your car suspension system. I'm gonna show it why by plotting. when I apply impulse input. It's good for car suspension system, but I'm not teaching you, only showing you now. Because if your car is under damp system, okay, after a bump, which is impulse, you're gonna have this response. And you feel it every day. Every single day you're driving your car, after passing bump as impulse input to your car, your body feels this, okay? But this is not good for robotics, because when your robot works in industrial section, you don't want that the end effector of the robot sees such oscillation, because you're in the danger of colliding with another object. You got what I mean, sir? Yes? Okay, so we don't want to design a controller that runs your robot by having a pair of complex conjugate poles. We don't want to have that. Not at all. Depends on your application that you want to control. Okay? For your car cruise that you are using in the highway, it's a set point. We say set point, like as a step unit, like as a step function. You set it on to 75 mile per hour. You are driving to San Francisco. You don't want your car behaves like this. This is a complex conjugate poles behavior. I'm going to teach you why by mathematics. You don't want a car goes to 80 and then back to 75. We name this as overshoot in vibration and in control. What happening in reality in your car is this. Here we go. Starting from, I don't know, 0 to, we don't have 0, I mean from 20 to 75. See what I'm saying? Everybody? So, let's continue. Case B. I'm increasing a damping a little more. When I say damping ratio, I don't care what the system is. It's a RLC circuit. There we go. Where we are? Oh. It's RLC circuit. It's master spring damper, 2 times, whatever it is, I don't care. Okay. So zeta is 1. And the name of this is critically damped system, not under damped. You increase a little damping of the system. Okay, let's play with that. If that's the case, we got a second order system. We have 2 poles minus zeta omega n, still plus omega n, the original one, not the changed one. See here? The original one. Here we go. Okay. This was for case A, we did it. Okay. So when the zeta is 1, how much is this for God's sake from kindergarten? How much is that? 0. So you have 2 repeated real poles. You have no imaginary part. So you have P1 is minus zeta omega n, and you have P2 is minus zeta omega n. The name of is critically damped system. The example I just gave you for your car cruise system as a control problem is this. When you have repeated real poles, you never experience such vanishing oscillation. And sir, this critically damped system is suitable for robotics because the end effector slowly moves to the destination without oscillation. See what I'm saying? For cruise control system, you go here. So let me plot it here because We have to go to control. This is not vibration class again. So you have two poles here at minus, we are showing on each other. See, here we go. So this is two poles, critically damped system. And these are for what? Under damped system. But the good news is that in both scenarios, both of them are in the left-hand side. Means your system is stable or unstable? Huh? Stable. Okay, stable. You got it, everybody? Can I go to the last case? Good. Okay. C. In the literature of the vibration, robotic and control, if you add a little more your damping, is zeta is greater than 1. We're going to name it as over damped system. It's extra damp, over damped systems. It's over damped systems. So for over damped system, looking back to the high school, so we had two poles of the system, the original one minus zeta omega n plus minus omega n zeta square minus 1. So when zeta is greater than 1, obviously zeta square is greater than 1. So zeta square minus 1 also is greater. So this is positive number. So you have two, this is how we say, two distinct real poles. Distinct real poles. One of them is minus zeta omega n plus omega n zeta square minus 1, and the second one is minus zeta omega n minus omega n zeta square minus 1. So if I was talking about your car cruise system as a control problem, and you want to have a set point to be tracked by your car cruise system to 70 miles per hour, is the speed that you want to go, I show you a underdamped system is not good, because this is fun in your car. Here you had what? You had what? A pair of complex conjugate poles. Critically damp is good because slowly you go without this overshoot, you go here. This is what? This is a critically damped system. But for the over-damped system, over-damp means you have over-resistance. Okay, it's like as friction. If you increase, guys, friction between your hands too much, it's gonna take a long time that you rub your hands. See what I'm saying? Simple like that from your childhood memory. So over-damp gonna be much slower. Here, finally goes there, but much slower. So, and you have two distinct real poles. Now, based on the application, we're gonna play with zeta and omega to design controller, PID or lead lag controller. You see the whole story about the control, undergraduate control. So, I'm summarizing everything here. If zeta is smaller than 1, underdamped system, you have a pair of complex conjugate poles. Oh, let me show you here, guys. I'm sorry. So, here you have, you change the color, yeah, minus, so, yeah, this plus this value minus this value. So you're gonna have two distinct real poles here and here. Here you go. This is for overdamped system. This is for overdamped. This is critically damped. Let me change the color. And this complex conjugate is for underdamped. UD. But all of them, they are in the left hand side. It's good. It says next your system is stable. So P1 and P2 was minus zeta omega n, a pair of complex conjugate poles, omega d. Zeta is 1, P1 and P2. You have two repeated poles, real repeated poles. You have critically damped system. And the overdamped system, you have a pair of, two distinct real poles, minus zeta omega and plus minus omega and zeta squared minus 1. I don't want to solve for now, but I'm going to take you to the high school and just give you why. In the next class, you're going to see this vanishing oscillation happens for the underdamped. Just look at here, guys. I taught you about the Euler equation, even that you know it. Ei theta is equal to cosine theta plus I sine theta. That's right, this is Euler, remember? This I is coming from here. That's why for underdamped system, you're going to have oscillation harmonic. But it's being damped. Omega d is, remember, omega d was omega n is over minus theta. But being damped is natural frequency. That's why it's vanishing. I'm going to teach you mathematically in the next class. After done, I'm going to send you to the Simulink and MATLAB again. Clear, everybody? Yes? Good, guys. Thank you and see you next class. Okay?
Thank you, Professor.
Thank you, I appreciate it. You see that still my voice has a problem. Okay?